So in this video, we are going to cover implicit differentiation. And the best way to introduce that is to talk about a circle. So in 171, we learned that the equation x squared plus y squared equal to 25 would define a circle. It has a radius of 5 and it is centered at the origin. More specifically, it is that circle down there. But we also know that that circle is not a function because the graph of that circle fails the vertical line test. However, the top half of the circle by itself would define a function. So if we're only talking about this top half, that is a function. Similarly, if we were only talking about the bottom half, that is a function. So you can imagine if I only talk about the top half, that would pass the vertical line test. And similarly, if we're only talking about the bottom half, that would also pass the vertical line test because that vertical line only touches that purple part one time. Now we can find those two functions separately, the top and the bottom, if we take the equation x squared plus y squared is equal to 25 and we solve it for y. So solving for y, I'm going to subtract x squared from both sides. So I get that y squared is equal to 25 minus x squared. And then we'll need to come in and take the square root of both sides to cancel out the squared on the y. But when we square root both sides, we have to remember to do plus or minus in front of the square root. So when we solve for y, we get two separate equations. We get the positive equation, y is equal to the square root of 25 minus x squared. I'm just not putting the plus in front of that. I can. And we also get the negative equation that y is equal to the negative square root of 25 minus x squared. So the graph of the circle actually consists of two separate functions together. The positive one giving us the top half and the negative one giving us the bottom half. If we wanted to write an equation that showed both halves together, well, that would be the entire equation of the circle, x squared plus y squared is equal to 25. Now, let's say I wanted to know the slope of the circle at some point. Let's say, for example, the point 3, 4, which is on that circle. If I wanted to know the slope at that point 3, 4, well, we know how to find that slope. We would take the derivative of the top half, because that point is on the top half, and then we would plug in x is equal to 3, and we would be able to solve for dy dx. Similarly, if I wanted to know the slope of the circle at the point 3, negative 4, which is down there, then we would take the derivative of the bottom half equation, and then we would plug in our x value of 3, and then be able to find dy dx, our slope, using the derivative. However, it is possible for us to take the derivative of the entire equation of the circle, of this entire equation here. And we do that doing implicit differentiation. So we would take the derivative of the first term. We know how to take the derivative of x squared. We would take the derivative of the second term, which is where we have to be a little bit careful because there's a y in there. And then finally, we would take the derivative of the third term on the other side of the equation, and we know that would be 0. Now, I said we have to be careful when we take the derivative of that y squared because y is a function of x. There's composition in there. So hopefully that's reminding you of the chain rule. So generally speaking, if I'm trying to take the derivative of y to some power n, we still apply the power rule. We bring the exponent of n down. The new exponent on y would be 1 less, so that would be n minus 1. But chain rule says we have to come in and take the derivative of y. And the derivative of y is simply dy dx, or y prime. I encourage you to write dy dx instead of y prime because I don't want you to think that a y prime is a y. Those look a little bit too similar. So we're going to be using dy dx. So let's look at an example where we take the derivative of the entire equation of the circle implicitly. So I'm going to start off and just apply my derivative operator to each of the 3 terms of this equation. So we're going to take the derivative of the x squared, and then we'll take the derivative of the y squared, and then we'll take the derivative of the 25. So we've applied our derivative operator to all three terms in the equation. Now let's begin differentiating. The derivative of x squared with respect to x is simply 2x. We're used to taking derivatives that only have x in them. However, when we get to the derivative of y squared, we pull the exponent of the 2 down in front. The new exponent on y is 1, which we don't really have to write, but chain rule says we then have to come in and take the derivative of y, which is dy dx. And then finally, on the right side of the equation, the derivative of 25 is just 0. So just a subtle difference between what happened in the derivative of the first term and what happened in the derivative of the second term. In reality, both of them are using chain rule. So in both cases, I'm going to erase this for just 1 second. We pulled the exponent of the 2 down. The new exponent on x is 1, and we don't typically write that. Chain rule says we would then come in and multiply by the derivative of x, but the derivative of x is just 1. So we don't usually write that either. We just get 2x for the derivative of x squared. But we do the same thing with the y squared. We pull the exponent of the 2 down. The new exponent on y is 1. We don't usually write that. But chain rule says we then have to come in and multiply by the derivative of y, which is dy dx. And then I'll go ahead and write back the 0 on the other side of the equation from the derivative of 25. Now we were trying to find dy dx. So I'm now going to take this equation and we are going to solve for dy dx. So I'm going to subtract 2x from both sides of this equation. So I now have 2y dy dx is equal to a negative 2x. Because we came in and did minus 2x there and minus 2x here. And if we're trying to solve for dy dx, then I need to come in and divide both sides by 2y so that that will cancel. And so then that leaves us with dy dx is equal to negative 2x over 2y. And we can simplify that to get that dy dx is equal to negative x divided by y, because our 2's cancel. So we now have an expression that would give us the slope at any point on the circle. I no longer would have to think about just the top half of the circle or just the bottom half of the circle, because we started with an equation that was both halves of the circle and differentiated it implicitly to get dy dx. So now in example 2, we want to find the slope of the circle. Find the slope, that means find dy dx at the points 3, 4, and 3, negative 4. So dy dx at the point 3, 4, well, x is equal to 3 and y is equal to 4, and we just found the expression for dy dx. So then dy dx would be equal to negative 3 over 4. So that tells us that at this point up here, 3, 4, the slope of that green line is negative 3/4. Now let's go on to find dy dx at the point 3, negative 4. So this time we're doing the same thing, except we're still plugging in 3 for x, but now we're plugging in negative 4 for y. And we're plugging into here what we found for dy dx. So we have negative 3 over a negative 4. And this negative, mind you, is the negative that was already there. So the two negatives cancel and leave us with a positive 3/4. So what that means is that at the point 3, negative 4, which was this point down there, the slope of that line is a positive 3 over 4. And we can see that that blue line does have a positive slope and that the green line does have a negative slope. So the main thing to take away when you're finding derivatives implicitly is if you're finding the derivative of a term that only has x, you take that derivative like normal. But if you're finding the derivative of a term that has y in it, you would need to make sure you're applying the chain rule and that you're picking up that dy dx. Let's look at some more examples. Example 3a, we want to find the derivative of y to the third with respect to x. Notice that this does have a y in it, so we are expecting to be using the chain rule and seeing the dy dx. We begin by pulling the exponent of 3 down. The new exponent on y is 2. And then chain rule says we then have to come in and multiply by the derivative of the y to get dy dx. So I'm just going to clean this up. This derivative is 3y squared dy dx. Moving on to example 3b. Now let's take the derivative of x to the third. Well, there is no y in here, so I'm not expecting to see a dy dx. We bring the exponent of 3 down. The new exponent on x is 2. I don't have to do chain rule here because the derivative of x would just be 1. And we don't usually write that. So this is just a 3x squared. In example 3c, we want to take the derivative of x to the third times y to the fifth. We're going to have to use the product rule because we do have two functions being multiplied together here. So we are going to need to find f, g, f prime, and g prime. Once we have all four of those, the product rule says that the derivative of this product is f prime g plus g prime f. So our f is the first factor, which is just x to the third, and our g is the second factor, which is y to the fifth. Now let's go ahead and start taking their derivatives. The derivative of x to the third, we bring the 3 down. The new exponent on x is 2. Chain rule says multiply by the derivative of x, but the derivative of x is 1, so we don't have to write anything else. Now let's take the derivative of y to the fifth. We bring the 5 down. The new exponent on y is 4. Chain rule says we have to multiply by the derivative of y, which is dy dx. So now that we have all four pieces, let's go ahead and plug into f prime g. So that's 3x squared times g plus g prime f. So we're adding that to 5y to the fourth dy dx multiplied by f, which is x to the third. And now I'm just going to clean this up a little bit. The first term is simply 3x squared y to the fifth. And then the second term, I'm going to move the x to the third so it's not at the back. I'm just going to put it after this 5. That's 5x to the third, y to the fourth, dy dx. And that is our derivative. So here before example 4, we have some steps to follow to find dy dx by implicit differentiation. I'm going to go ahead and jump right into example 4a, and we will follow these steps as we work through example 4a. So in 4a, we want to find dy dx for this equation, y to the fourth plus x to the fourth minus 2x squared y squared is equal to 9. Step 1 tells us to differentiate both sides of the equation with respect to x. When differentiating a y, include dy dx. And we've already known that. We've seen that happen before. For instance, in example 3a, when we had a y show up, we did get a dy dx. In example 3b, there's no y, there's no dy dx. So let's start off by differentiating both sides of the equation. So I'm just going to come in and write a ddx in front of every term of the equation because we are taking the derivative of both sides of the equation with respect to x. So that's why we have that dx in front of these. So now let's go in and start differentiating. Starting with the first term, the derivative of y to the fourth, we'll bring the exponent of 4 down in front. The new exponent on y is 3. We had a y, so chain rule tells us that we need to put a dy dx there. Moving on to the derivative of x to the fourth. There's no y in this term, so we'll take this derivative as normal, simply 4x cubed. Now, when we get to this derivative of 2x squared y squared, we will have to come in and use the product rule to take that derivative because we do have two terms being multiplied together there. I am going to go ahead and put a minus there and open up parentheses here. Be careful because this minus, you want to make sure that we're going to distribute that negative when we actually do come in here and fill out f prime g plus g prime f. So f is 2x squared, g is y squared. So I've picked two different factors that are in that product, and now let's go take the derivative of both of them. F prime is 4x, g prime is 2y dy dx. So we brought the derivative of we brought the exponent of 2 down, the new exponent on y is 1, and we pick up that dy dx. So now I'm ready to come in here and fill out f prime g, so that's 4x times y squared plus g prime f. So I'm multiplying f with g prime. So multiplying those 2's will give us a 4. I'll go ahead and put the x squared and then the y and then the dy dx. On the other side of the equation, the derivative of 9 is simply 0. So now what I'm going to do is I'm going to go ahead and just distribute this negative in, just do a little bit of algebra in here. So I'll bring down everything that we already had. We now have a negative 4x y squared and a negative 4x squared y dy dx, and that's equal to 0. So we have completed the first step. We have taken the derivative on both sides with respect to x, and any term that had a y, we did see a dy dx show up in. Step 2 says to collect all terms involving dy dx on one side and all others on the other side. It doesn't matter which side of the equation you choose to put your dy dx's on. I'm going to choose to put my dy dx's on the left. So everything that does not have a dy dx is going to go to the right side of the equation. Well, this 4x cubed term does not have a dy dx, so I'm going to move it. And this negative 4x y squared does not have a dy dx, so I'm going to move it. So I'm adding that to cancel it out from the left side of the equation. So now let's write what we are left with. That is 4y cubed dy dx minus 4x squared y dy dx is equal to a negative 4x cubed plus 4x y squared. And you could rearrange the terms on the right side if you wanted to, so we're not seeing that negative term first. We could write the 4x y squared minus 4x cubed. Either way is fine. So now we've done step 2. We have all the terms that have dy dx on one side of the equation, and then all the terms with no dy dx are on the other side of the equation. So now we're on to step 3 that tells us to factor out the dy dx. So the terms on the left side have the dy dx. We're going to factor that dy dx out. What it leaves us with in parentheses is the 4y cubed minus 4x squared y. So everything that got left after we pulled out that dy dx. I'll write what's left on the other side of the equation. So now that we factored out the dy dx, now we need to solve for it by dividing. So we'll solve for that by simply dividing by everything we have on the inside of those parentheses. So we are left with dy dx is equal to 4x y squared minus 4x cubed divided by 4y cubed minus 4x squared y. And so this is our answer to part A, to find dy dx. So we take the derivative of each term. We make sure that we're putting a dy dx if we see y terms. We get all the terms that have dy dx on the same side of the equation. Doesn't matter if you put them on the left side or the right side. And all the terms that do not have dy dx on the other side of the equation. On the side that does have the dy dx terms, you factor that dy dx out. And then to solve for it, you divide by whatever is left in parentheses. Part B is asking us to evaluate dy dx when x is equal to 2 and when y is equal to 1. So when x is equal to 2 and y is equal to 1, we are going to plug those values into dy dx, this expression down here. So in the numerator, we would have 4 times x, so that's times 2, times y squared, so times 1 squared, minus 4x cubed, so that's 4 times 2 cubed, divided by 4y cubed, so that's 4 times 1 cubed, minus 4x squared is 2 squared, times y is 1. And now we will simplify this. So 4 times 2 times 1 squared is 8, minus 4 times 2 cubed is a minus 32. In the denominator, 4 times 1 is 4, minus 4 times 2 squared is 16. So simplifying this, 8 minus 32 is a negative 24, 4 minus 16 is a negative 12, and negative 24 divided by negative 12 leaves us with a positive 2. In example 5, we have a demand equation. X is equal to the square root of 1900 minus p cubed. We want to use implicit differentiation to find dp dx, and then evaluate it at p is equal to 10 and interpret our answer. So in this example, think of our p as being y. So p is our dependent variable in this case, and x is still our independent variable. So we're going to find dp dx, and one indication that we will have to use implicit differentiation is that this is not solved explicitly for p, right? It's not solved for y, right? So I'm going to go in and start differentiating both sides of the equation. So we'll take the derivative of the left side, which is just x, and then we'll take the derivative of the right side. I'm going to rewrite the right side as 1900 minus p cubed all to the 1/2 power, since it's under the square root. So let's start differentiating. On the left side, the derivative of x is just 1. On the right side, we're going to bring down the exponent of 1/2. The new exponent of everything that's on the inside of those parentheses will be 1 less, so a negative 1/2. And then chain rule tells us that we need to multiply by the derivative of the inside. And I'm just going to write that like this for now. And then in the next line, we'll actually talk about what that derivative is. So I'll bring down the 1, the 1/2, the 1900 minus p cubed to the negative 1/2. And then the derivative of that 1900 minus p cubed, well, the derivative of 1900 is just 0. For the negative p cubed, we'll bring down the exponent of 3. The new exponent on p is 2. And this is not just x, so chain rule tells us we need to have a dp dx, okay? Because p is a function of x in this case. So the p is like the y in this example. So remember, this whole time we've been saying every time we see a y, we have a dy dx. So similarly here, every time we see a p, we have a dp dx. So we have differentiated. Let's go ahead and find dp dx. So I want to solve for dp dx. I'm going to just rewrite this so it looks a little bit better. So I have 1 over 2. This whole term right here had this negative 1/2 exponent. So I'm going to rewrite that in the denominator under the square root. And then the negative p squared, negative 3p squared dp dx. I'm going to put that negative 3p squared in the top. And I'll just leave the dp dx out on the end. I could have multiplied it up in the numerator, but we're trying to solve for it, so I'm just going to kind of write it off to the side there, because it makes it a little bit easier to see that to solve for that, I need to come in on both sides of the equation, I'm trying to get rid of this fraction. We want to divide by that fraction, which is the same as multiplying by the reciprocal. So I'm multiplying both sides by 2 times the square root of 1900 minus p cubed divided by a negative 3p squared. And we need to do that on both sides of the equation. So we're now left with the denominator here canceling and the negative 3p squared canceling. I'll start with the left side first because that's what we're trying to solve for. So now we have dp dx equals just that fraction that we have on the left side in purple. I think I said earlier I'll start with the left side, but I really started with the right side because we're trying to solve for that dp dx. This was all just multiplied by 1, and so nothing changes. So here is dp dx. We are then asked to evaluate it at p is equal to 10. So now I'm just going to be plugging in 10. So at p is equal to 10, dp dx equals 2 times the square root of 1900 minus 10 cubed over negative 3 times 10 squared. So this is 2 times the square root of 1900 minus 1000, which is 900, over negative 3 times 10 squared, which is negative 300. The square root of 900 is 30. So this is 2 times 30 over negative 300. And then I'll just simplify this. 30 goes into 30 once. 30 goes into 300 10 times. So this leaves us with a negative 2 over 10, which is a negative 1/5. And now we're going to interpret this. So in this problem, we had this demand equation. The demand is showing how much people are demanding this product. So our X is the quantity of whatever is being sold, and the P is the price for which it is being sold. So we calculated that dp dx is equal to negative 0.2. So this means that the rate of change, now the rate of change of what? So we're talking about dp dx. So the rate of change of the price of P in the numerator with respect to what's in the denominator, which is X, and X represents the quantity, is negative 0.2. So in other words, that is telling us that when we have, or rather I'll phrase it like this, so that increasing the quantity by 1, that's 1 change in X, means decreasing the price by 20 cents. And it's a decrease because dp dx was negative. So in other words, each 20-cent price decrease brings about one more sale at the given value of P.